friends, IBM is here with physics, and I just wanted to conclude astrophysics and cosmology by taking you through the last consolidation test which I gave to my students. And this is physics 9702 paper 4, that is advanced structured equations, and so advanced structured equations, that is AL. This is just a supplementary video on astrophysics and cosmology. And without wasting time, I want to take you to the test which I gave to my students about new past paper questions that I tested with my students, and therefore I decided to record a video about it. So without wasting time, here is the test, and I called it consolidation test because it is the final test in astrophysics and cosmology. Number 1, name the term used to describe an astronomical object that has a known luminosity. We said an astronomical object that has a known luminosity is called a standard candle. So this is a standard candle. Determine the distance of the star from the Earth. So a star has a known luminosity, which is that one, so it is a standard candle. A scientist observing this star finds that the radiant flux intensity of light on Earth from the star is 2.6 nanowatts per meter squared. So determine the distance of the star from the Earth. So the radiant flux intensity F is equal to the luminosity divided by 4 pi d squared. They have given us the luminosity. We have the radiant flux intensity, so we just substitute to find d. So substituting, the radiant flux intensity will be 2.6 times 10 power negative 9. This is equal to the luminosity because I multiplied by negative 9 because of the nano, that is 2.6 nanowatts per meter squared. Then the luminosity is going to be 4.8 times 10 power 29 divided by 4 pi times d squared. Of course, making d the subject, this is going to be the square root of 4.8 times 10 power 29 divided by 4 pi times 2.6 times 10 power negative 9. So I turn to my calculator. So my calculator gives me 3.8 times 10 power 18 meters. The sun has a surface temperature of 5,800 Kelvin. The wavelength lambda max of light from which the maximum rate of emission occurs is 500 nanometers. The scientist observing the star in A finds that the wavelength for which maximum rate of emission occurs from the star is 430 nanometers. Show that the surface temperature of the star is approximately 6,700 Kelvin. Explain your reasoning. So I'll just use Wien's displacement law. That is my reasoning by Wien's displacement law. Remember, according to Wien's law, the wavelength at which maximum intensity occurs, or the wavelength at which maximum intensity is emitted, is inversely proportional to the absolute temperature. That is lambda max. Remember, lambda max is not maximum wavelength, but is wavelength at which maximum intensity occurs. So I will have two equations using this expression. Lambda max times T should be a constant. So for the sun, I'll have that 500 nanometers times the temperature, which is 5,800 Kelvin, should be equal to a constant. Then for the star, the wavelength is 430 nanometers times the temperature which I want should be equal to the same constant because lambda max times T is a constant. So if I make T the subject, T is going to be 500. T is going to be 500 divided by 430, then times 5800 Kelvin. So I'll check my calculator. 500 divided by 430 times 5800. So from my calculator, I'm getting T as 6,744 point something, or which is approximately 6,700 Kelvin. Use the information in A and B Roman 1 to determine the radius of the star. Of course, the luminosity of the star L is given by the area, which is 4 pi r squared times Stefan-Boltzmann's constant times T power 4. The luminosity has been given above there as 4.8 times 10 power 29. So I'll have that 4.8 times 10 power 29 is equal to 4 pi times r squared times Stefan-Boltzmann's constant sigma is 5.67 times 10 power negative 8 times the temperature power 4, and the temperature is 6,700 raised to power 4. So I make R the subject. I'll just press my calculator. So from my calculator, I am having 1.8 times 10 power 10 in meters. 1.8 times 10 power 10 in meters. State what is meant by a luminosity of a star. Luminosity of a star. So luminosity, of course, luminosity is the total radiant power emitted by the star. The total radiant power emitted by a star. Luminosity is the total radiant power emitted by a star. Because power is energy over time, we could also define luminosity as the total radiant energy per unit time emitted by a star. The luminosity of the sun is 3.8 times 10 power 26 watts. The distance between the earth and the sun is 1.5 times 1.51 times 10 power 11 meters. Sometimes this is called the astronomical unit, the average earth to sun distance. Calculate the radiant flux intensity F of the sun at the earth. Give a unit with your answer. So F is given by the luminosity divided by 4 pi times d squared. The luminosity is 3.83 times 10 power 26 divided by 4 pi times d, which d is 1.51 times 10 power 11, and this should be squared. So I will just check my calculator. So from my calculator, I have 1340, and the unit is, of course, it is power per unit area. Radiant flux intensity is total power passing normally through a surface per unit area. So that is going to be watts per meter squared. Use data from B to calculate the mass that is converted into energy every second. the mass that is converted into energy every second. Of course, we know that power is equal to energy. Power is energy over time. That is power. Power is energy over time, but energy is going to be equal to actually mass mc squared. So I will divide this one by T. So we want the mass converted into energy every second. So we want mass in every second, time is 1 second. So m over T, T is 1 second. So the mass converted, or mass per unit time converted in 1 second, will actually be equal to the power divided by c squared. So this will be equal to power is, remember the power is actually the luminosity. The power is the luminosity, which is 3.83 times 10 power 26. The power is the luminosity because it is, you see that it is in watts. Then divide by c squared, which is 3.0 times 10 power 8, and this is squared. I press my calculator. From my calculator, this gives me 4.26 times 10 power 9 kilograms. It is actually kilograms per second. Okay, the radius of the sun is 6.96 times 10 power 80 meters. Show that the temperature T of the surface of the sun is 5770. Okay, so we just know that luminosity. This equation is normally given, the list of formula. Luminosity is 4 pi as sigma r squared T power 4. So we just substitute, the luminosity is given as 3.8 times 10 power 26. This should be equal to 4 pi. Sigma is 5.67 times 10 power negative 8. The radius has been given as 6.96 times 10 power 18. And this should be squared, then times T power 4. I'll just press my calculator and make T the subject. So from my calculator, this is exact. This is 3 significant figures, 5770 Kelvin. The wavelength of light for which the maximum rate of emission occurs from the sun is 5.00 times 10 power negative 7. The temperature of the surface of the star is Sirius is 9940. Use information from D to determine the wavelength of light for which the maximum rate of emission occurs. So here we shall just use Wien's displacement law. The wavelength at which maximum intensity occurs is inversely proportional to the absolute temperature. So I'll come up with two equations. The wavelength lambda max of light for which maximum rate of emission occurs from the sun is that. So lambda times T should be equal to a constant. So the wavelength is 5.00 times 10 power negative 7. The temperature of the sun is 5770. This is equal to a constant. Then for the star Sirius, the wavelength is not known. I'll call that one lambda times the surface temperature, which is 9940. This should be called the same constant. So we divide the two equations. And when we divide the two equations and make lambda the subject, we realize that lambda is going to be equal to 5770 over 9940 times 5.00 times 10 power negative 7. I turn to my calculator. So from my calculator, I have obtained 2.90 times 10 power negative 7. Okay, next. State Wien's displacement law. Of course, Wien's displacement law states that the wavelength at which maximum intensity occurs is inversely proportional to the thermodynamic temperature or absolute temperature. So the wavelength at maximum intensity. The wavelength at which maximum intensity occurs is inversely proportional. Is inversely proportional to the thermodynamic temperature. The figure shows the wavelength distributions of electromagnetic radiation emitted by two stars. So we see star A and star B. You see the peak of star A is around here. I think it is at 0.65. And the peak of star B is around here, which I think is 0.65. This is 0.5, the other one is 0.65. The surface temperature of star A is known to be 5,800. Perhaps it is the sun. Determine the surface temperature of star B. So, of course, by Wien's displacement law, the wavelength at which maximum intensity occurs is inversely proportional to the absolute temperature. I will come up with two equations using star A. The wavelength of star A is 0.5. I will not convert. 0.5 micrometers times the surface temperature, which is 5,800, should be equal to a constant. Then I consider star B. The wavelength of star B is, I think this is 0.65 using the scale. 0.65 times the surface temperature, which I don't know, should be equal to the same constant. I make T the subject. T is going to be equal to 0.50 divided by 0.65 times 5,800. I just made T the constant, the subject, by either equating these two equations or by dividing. I turn to my calculator. So from my calculator, two significant figures, I have 4,500 Kelvin. Star B appears less bright than star A when viewed from the Earth. Use the figure to suggest with a reason how else the physical appearance of star B compares with that of star A. So when you look at star B and star A, we see that star B has a longer wavelength. Maximum intensity is occurring at a longer wavelength, which means also even when you look at the values, the value of temperature, you see that star A is having a higher temperature than star B. Remember, hotter stars are bluish, or they tend to be blue, and cooler stars are going to be reddish. What does that mean? Star B is going to look redder than star A because star B is cooler than star A. You see that star B has a greater average wavelength, which is around 0.65. So it is having a longer wavelength, therefore it is redder than star A. So you can say star B has a greater average wavelength. So star B looks redder. So star B looks redder. Okay, then last page. The lines in the figure 10.1 have been corrected for redshift. State what is meant by redshift. Of course, redshift is the apparent increase in wavelength or decrease in frequency. Redshift is the apparent increase or the fractional increase. The fractional increase in wavelength of light due to the source and the observer I think observer ends with O, and the observer receding, that is moving away from each other. If the observer and the source were moving towards each other, we would call it a blue shift. But since they are moving away from each other, that is a red shift. Explain how cosmologists are able to determine the light from that light from a distant star has undergone a redshift. Of course, cosmologists that just look at the spectral lines in light from distant stars, and they compare the positions of these spectral lines with their known positions in the laboratory. So by examining the lines, that is the spectral lines, the lines in the spectrum, of light from stars, and comparing with the known spectrum. So cosmologists will just look at the lines in the spectrum of light from stars and then try to compare them with the known spectrum in the laboratory. Lastly, state Hubble's law. I think Hubble's law is simply V is equal to H naught times D. In other words, V is directly proportional to D. So Hubble's law states that the recessional speed of a galaxy, recessional to recede is to move away. The recessional speed of a galaxy is directly proportional to its distance from the Earth. Explain how cosmologists use observations of emission spectra from stars in distant galaxies to determine that the universe is expanding. Of course, this is related to the redshift, but of course, the wavelength of spectral lines are actually greater than their known values in the laboratory. the wavelengths of spectral lines are greater than their known values. Their known values in the laboratory. So this redshift shows that that stars in distant galaxies are moving away from the Earth. This redshift shows that stars in distant galaxies are moving away. Are moving away from the Earth. Since the stars themselves do not move, perhaps it is the universe which is expanding. So the redshift shows that the stars in distant galaxies are actually moving away from the Earth. But since, remember, the stars themselves do not move, perhaps it is the galaxies in which they are that are moving. Last but not least, explain how Hubble's law and the idea of the expanding universe lead to the Big Bang theory. How does Hubble's law and the idea of the expanding universe lead to the Big Bang theory? Remember, all parts of the universe are moving out from each other. All parts of the universe are moving away from each other. All parts of the universe are moving out from each other. And we can believe from Hubble's law that the more distant objects must be moving away faster because the speed is directly proportional to the distance from the Earth. So according to Hubble's law, the more distant objects are moving away faster. More distant objects are moving away faster. So according to the Big Bang theory, matter, since everything is moving away, then matter and everything else must have started from the same singular point. So matter must have been close together in a very dense singular point in the past. So that is how Hubble's law and the idea of the expanding universe lead to the Big Bang theory. If all parts of the universe are moving away from each other and the more distant objects are believed to be moving faster according to Hubble's law, then everything else must have started from the same singular point as predicted by the Big Bang theory. So that is officially the end of astrophysics, and I hope this video has been helpful. I couldn't record a long video for quantum physics now because I have flu, but tomorrow I'll be on it. Thank you and stay blessed.